Okay, this is VLSI data conversion circuits, lecture 44. In the last class we were looking at how one could reduce the offset of a latch. Please realize that the latch in itself is some pretty complicated circuitry inside that box, which operates with a whole bunch of clock phases and so on, and finally gives out a decision D. And we also understand that the latch is working off a sample of the input, right. It is not a continuous time comparator. What it is doing is it is sampling the input implicitly and figuring out if that differential input is greater than 0 or smaller than 0. And due to device mismatch, we have static and dynamic offsets, and the offset can only be minimized by increasing the size of the devices, which will in turn increase the power dissipation. So what we then decided was to say, if the latch has an input referred offset that can be reduced by a factor A if one puts in front of the latch an amplifier with a gain A. Unfortunately now the amplifier with a gain A will have offset in itself simply because it is also made with transistors, and these transistors are also likely to be mismatched. And again one could reduce the input referred offset of the amplifier by making the device sizes larger and larger and larger. However, this carries the penalties of A, power dissipation, and 2, while it is true that you indeed burn more power in this amplifier, the input capacitance of the amplifier will also increase, which means that the stage driving the comparator, which is basically what is driving this array of comparators? The sample and hold, which drives the array of comparators, now has to drive a much larger load capacitance, which in turn will mean that it has to burn a lot more power, because a larger capacitance has to be charged to the same voltage, which means that there is a lot more current flowing through the capacitor, right. So brute forcing it by deliberately making the offset low does not seem like a very attractive solution, right. And understanding that this is a we are working off of samples, one can say that during some part of time the latch is actually amplifying the difference between its inputs, okay, and at that time the output of the amplifier before the latch is not really necessary, correct. So the latch is reading or observing the output of the amplifier which occurs before the latch, right, and which is why this is called a pre-amplifier. The pre-amplifier output is being observed by the latch only when during some part of the clock period. Once the latch samples the output of the pre-amplifier, it regenerates the output, correct, and during that time what is happening? The pre-amplifier's output is not really necessary, which means that we indeed have time to do some housekeeping, right. So that time can be used to estimate the offset of the preamp and subtract it off, right. So that is the basic idea behind the whole thing. And the last time around we were trying to look at one way of cancelling offset. So this is called the pre-amplifier, and please note that the timing of the pre-amplifier and the latch has to be carefully managed, because the output of the preamplifier must be sampled at the right time, and then the offset correction in the preamplifier must happen precisely when the latch is busy regenerating and making a decision and all that stuff. Okay. So, the basic idea behind the preamp, as we saw the last time around for a single ended example, was to say let us assume that we have an amplifier with an offset V off, and to estimate the offset of the amplifier, what one would do would be the following: measuring the output voltage of the amplifier when the input is set to 0, one would naively conclude that the output would be A times V offset. Unfortunately, that is not true in practice, because if the gain A is large, the output of the amplifier will simply saturate, thereby giving us no information at all about the offset, correct, except perhaps the sign. So, the next idea was to say, we know that if we place the offset the amplifier in a feedback loop, in this case specially chosen to be unity feedback, then the output voltage of the amplifier will be approximately V offset. Exactly what will it be? It will be, for this particular sign of offset chosen, it will be minus V offset times A by A plus 1. And as we see, for A being a large number, this voltage developed at the output of the preamplifier is virtually equal to minus V offset. Okay. So, during this special phase called the auto zero phase, what we are doing is A, creating a negative feedback loop around the preamplifier, right, estimating the offset which is now developed at the output, holding that on a, that information must be stored for further use, and in analog, if you want to store a quantity, it must either be done with inductors or capacitors, and inductors are out of the picture. So, must be done with capacitors. Okay. So, as we saw the last time around, the capacitance CAZ is used to store the offset. So, at the end of the auto zero phase, what is the voltage across CAZ? The voltage across CAZ at the end of phi AZ is nothing but minus V offset times A by A plus 1, correct. Now, if we open the auto zero switches, notice the following: this voltage is approximately minus V offset, correct, and this voltage is also minus V offset, thereby the same voltage is now applied to both the terminals, which means that in effect the difference is almost offset free. I mean, the reason why it is almost offset free is that the voltage across the capacitor is not exactly minus V offset, but A by A plus 1 times V offset, which is a number which is very close to 1. Okay. So, once the offset has been stored on this capacitor CAZ, the next job is to apply the input, and that is straightforward. As we saw last time, So, the equivalent circuit in the amplify phase, which is phi Az complement, will be V in, this is V offset, this voltage is V offset times A by A plus 1, and the output voltage will therefore be A times V in minus V offset divided by A plus 1. Okay. So, we can see that if A is sufficiently large, the input referred offset of the preamplifier has been reduced by a factor of A plus 1, which is approximately the DC gain of the amplifier. All right. So, it is important to make A very large. While this is the basic idea, you must recall that we are now dealing with fully differential signals, correct, and therefore, we must figure out a way of implementing a differential preamp, where the output of the preamplifier is a difference between two node voltages. It is not referred to ground like the way we show here. You understand, this output voltage by implication here means that it is reference to ground, whereas the latch is receiving a differential set of inputs, which means that the output of the preamp must also be differential. So, let us now see how one can realize something like that. So, in other words, what we are after is a preamp whose differential output voltage is A times, if we call this VIP and VIM, VOM and VOP, then VOP minus VOM is some A times VIP minus VI. Does it make sense? All right. And again there will be offset and so on, and we can use similar techniques that we have just discussed for the differential case. To illustrate that, let us assume that this preamplifier is plagued with offset of this nature. In other words, VOP minus VOM is A times VIP minus VIM minus V offset. Please note the departure from the earlier case. this is only saying that the difference between the two output voltages is A times the difference between the inputs. There is no statement made as yet about the absolute voltage at the output in relation to either the differential input or the absolute voltages at the input. Is this clear? All right. Now, what do you think one can do to estimate offset? Again the same idea. So, during the auto 0 phase we put this amplifier in a unity feedback loop. Now, what is the idea behind the unity feedback loop? Correct. The differential VOP minus VOM must be connected to the differential input. Please note what was happening in the single ended case. Let me redraw that. Right. So, the negative input of the amplifier was being connected to the output, correct. Now, the differential input must be connected in an inverted fashion to the differential output. Okay. So, that means that during the auto 0 phase the amplifier is now placed in a unity gain feedback loop as shown here. What will be the differential output now? Let us just calculate. How do you do this? What is the difference between these two nodes?
It's 0.
No.
VIP minus VI minus.
Okay, let us just simply calculate this. So, the positive terminal of the preamp input has a potential which is VOM minus V offset, correct. This minus VOP times A must be equal to VOP minus VOM, which means that VOP minus VOM must be equal to minus V offset times A by A plus 1, just like in the single ended case. Does it make sense? Okay. So, the difference between VOP and VOM during the auto 0 phase is minus V offset times A by A plus 1, and for a sufficiently large A this difference will be minus V offset, correct. Now, the next job is to store this differential offset. Again, please note that the offset is not stored either as the absolute potential of the output P or output M. The offset information is stored as the difference between the two voltages, okay. So, which means that it is not enough to just hold VOP or VOM, we need to hold both the output voltages, simply because the information, the offset we are after, is stored as the difference between the two. So what do you think we can do? Pardon? Okay, we need a capacitor at VIP and VIM. One way to do this is to say I am going to hold VOM on one capacitor, hold VOP on another capacitor, okay, and I will explain the reasons for choosing this over what he suggested in a couple of minutes. Okay. So this is phi AZ, phi AZ, CAZ, CAZ. Okay. Let me call this V bias. Okay. So what is the voltage across CAZ at the end of the auto zero phase? Pardon? The voltage across the auto zero capacitor CAZ at the end of the auto zero phase is VOM. I mean, as usual we define this to be the positive terminal. So, VOM minus V bias, and then the other one will be VOP minus V bias, correct. So, the absolute voltages across the two capacitors still have will have within quotes no meaning, right. The information we are after is what? VOP minus VOM, and therefore that is still available as the difference in the voltages across the two capacitors, correct. So, please note that the offset is stored as information on the difference between these two voltages. Now, we need to add the input. So, what do you suggest I do? As usual, based on our experience with the single ended example, connect this here, and what are connected to the left side? To prevent abuse of notation, I will say V we sample and hold P and we sample and hold N. Okay. Where the understanding is that the inputs come from the sample and hold. All right. As we can see, the offset cancellation is not affected in any way by the absolute value of V bias we choose. correct, because the voltage difference between the two capacitors remains equal to V offset into A by A plus 1 regardless of the value of V bias, because V bias is common to both sides. Now, one feature of this fully differential preamp is that it is a symmetric structure about this axis, which means that the layout will be symmetric and the parasitics will be symmetric, at least in principle, on both sides of VSP and VSM. Okay. One suggestion made was, why don't you put one single auto zero capacitor across the two inputs and then move it in series with, you understand, this is another conceivable approach, which is to say, as usual, this is phi a z, and one could in principle store the offset on this capacitor C A Z, right, and then do what? Put this capacitor, for instance, in series with one of the inputs, whereas we SM goes in to the other. In principle, this should work, correct. Unfortunately, there are several practical problems with this. There is the layout issue of both paths not being exactly symmetric. Another important point is that of charge injection, right. So, we have dealt with charge injection in depth before, and the origin of charge injection is that every MOSFET conducts when there is charge in the channel. When you turn it off, this charge has to go out through the source and drain, and it is not exactly clear how much goes where unless you carefully look at the various impedances of both nodes and calculate and stuff. Okay. So, here for instance, consider this. What do you think is a good idea to avoid charge injection from these switches? Do you think it particularly matters which is turned off first? Do you follow my question? So, at the end of the auto zero phase, we need to turn off these switches, correct. Now, you can either turn off the feedback path switches first or the bias path switches first. Which do you think is a better idea? And why? mean, how many ways is there of doing this?
Only two ways.
You either turn off the bias switches first or the feedback switches first. If we turn off the bias switches first, what happens?
I mean, if we turn on the bias switches first, there will be charge injection,
Correct?
and that current has a path to flow through the capacitor,
Yes.
and then the feedback switch, and then to ground through the amplifier.
Sure. Okay.
So if we switch out the feedback switches first, then that. No, yeah. If we
If we switch off the bias path switches first, there will be charge injection. Can you comment on the charge injection on both paths? I mean, in the absence of mismatch in the switches, the same amount of charge will go on to both the capacitors, right? So there will be a change in the capacitor voltages. However, the change is the same in both the paths, which means that the differential voltage across the capacitors does not change. Is that clear? And why is the switch charge injection the same in both cases? Because the gate source voltage of the switches is the same, and that is equal to VDD minus V bias minus VT will be the gate overdrive, right. So even though there is charge injection, that charge injection is a common mode affair because it affects both paths to the same degree, right. All right. So if on the other hand one turned off the feedback path switches, what do you think will happen?
slightly different.
The gate source voltage is mildly different, okay, because one of them VOP and VOM are slightly different by approximately V offset, correct. So one could argue that there is nothing to choose. You can either make one turn off earlier or the other one turn off earlier, or you use the same clock for both and you do not really care which turns off earlier, okay. However, please recall that we also need to subtract. This preamplifier will only compare VSP and VSM, it will amplify the difference between VSP and VSM, but what are we after for the complete comparator? I mean, how will you build the flash? Is there something else we need to do or what? We need to subtract the references also, correct. So the last time around what did we do in the single ended case? How did we subtract the reference? We said instead of, I mean, the top plate of the capacitor was sampling the offset of the at the output of the amplifier, which was in the unity gain feedback loop. The lower plate was connected to a reference, so the true voltage stored across that auto zero capacitor was the reference plus offset, okay. All right. So the same thing can be done here also. Now by analogy, what do you think, how will you subtract the references?
Replace V bias.
Replace V bias by Vref P and Vref M. So what is the differential voltage stored across the auto zero capacitors? So let us call this the capacitor on top has a voltage VOM minus Vref P, the lower capacitor has got a voltage VOP minus Vref M, which means the difference is nothing but VOM minus VOP minus Vref P minus Vref, and VOM minus VOP is nothing but V offset by times A by A plus 1. Is this clear? So, the differential voltages after the auto zero phase is done, the difference between the two preamp inputs is therefore VSP plus VOM minus Vref P, right, minus VSM plus VOP minus Vref M which is given by VSP minus VSM minus VOP minus VOM minus Vref P minus Vref M. So, VOP minus VOM is nothing but please note that this VOP minus VOM refers to the output of the preamp at the end of the auto zero phase and is therefore equal to minus V offset times A by A plus 1, correct. So, this is VIP minus VI. Is this clear? All right. So, the difference between those two nodes, please note that this node here is a fictitious node, it is not really available to us, correct. So, the difference between this node and this node will therefore be
It should be
minus V offset by A plus A.
Yes, correct. So, the which means that the output of the preamplifier will be VOP minus VOM is nothing but VSP minus VSM, which is the differential input minus the differential reference minus V offset by A plus 1. Okay. Because the difference between these two voltages was VSP minus VSM minus VRFP minus VRFM plus V offset times A by A plus 1. Now you have minus V offset. So, the residual offset is only V offset by A plus 1. This is exactly analogous to what was there in the single ended case. Is this clear? So, the preamp has effectively made two contributions. One, the large gain has resulted in an effective reduction of the offset of the latch by this factor. Then the capacitors which were used to hold the offset can also be used to store the references. So, subtraction of the references is also a very straightforward affair. You understand? Now, a couple of things. Now, can you tell me which of these switches you will turn off first? So, there are switches in the reference path and there are switches in the feedback path. Based on the reasoning we had earlier, which do you think you want to turn off first now? The feedback, and why does that make sense?
Because the VRFP and VRFM may not be same.
Correct. So, if you go across the entire flash array, clearly VRFP and VRFM are changing, correct, all the way from negative full scale to positive full scale. Now, if you turn off the reference path switches first, the charge injection will not be the same. The difference in charge will be proportional to VRFP minus VRFM. So, as you go from the lowest comparator all the way to the topmost comparator, since the charge injection is now dependent in some nonlinear fashion on VRFP minus VRFM, you will find that the references which are stored on these auto zero capacitors are corrupted by some nonlinear error. On the other hand, if you open the feedback path switches first, you will find that the charge injected is virtually the same, because we assume that V offset is a small quantity, right, and the charge injection is therefore even though it is different, is very small and is not a problem. Is this clear? The next thing I want to bring to your attention is that yes.
This VOP minus VFM and this expression should be multiplied by A, right?
Oh yes, sorry. Yes, indeed. Thank you. So, this will be multiplied by minus A, I believe. Does this make sense? So, the preamp is amplifying the difference between a differential input and a differential reference, causing the output to build up hopefully to a large voltage, which is enough to overcome the offset of the latch. the next thing I want to bring to your attention is the following. What do you think we should choose these capacitances to be? Should they be very large? Can they be very small? Okay, and why do you think it must be chosen to be large?
It must be it has to be large because any leakage or any charge, any leakage current at the input of the amplifier might discharge this capacitor.
Okay, so again let us go back to the single ended version just for convenience. To understand the principles involved in order to be able to make an informed decision on the size of the auto zero capacitor. All right. So, you want to make it large and why is that? What are the advantages of choosing a large capacitance?
We are sampling some noise.
Pardon? Okay, all right. So, one thing that he mentions is the following. Please note that the amplifier will have some input parasitic, isn't it? So, let us call this Cp, all right. Now, what is the effect of Cp?
Because there is a capacitance, your signal will get attenuated.
Okay. So, and during which phase is Cp problematic?
5 AZ bar.
So, during the amplify phase, right, the effective circuit looks like this. So, this is CAZ, this is Cp and this is the preamp, okay, and this is Vi. So, what is this voltage? So, this is nothing but CAZ by CAZ plus Cp times Vi and is therefore
Much greater than CP.
in order to not attenuate the input signal. If you attenuate the input signal, it is basically like having a smaller gain in the amplifier, isn't it? So, you want it large so that this factor CAZ by CAZ plus Cp is close to 1. Are there any other reasons why you would want CAZ to be large?
Any leakage current.
Correct. Please note that all these switches are MOS switches and all MOS devices have leakage due to a junction, I mean the source drain, sorry, the source bulk and the drain bulk junctions after all are reverse bias diodes. So, they will have small but finite leakage currents. So, if you take a very small capacitor, right, stuff is likely to leak away. But do you think this is a real problem? I mean, if this has to really affect you, I mean, what time scales are we interested in? I mean, sure, what I am trying to say is that, yeah, if you take this capacitor, charge it up, and then you come back tomorrow, obviously, there is not going to be, any charge left on the capacitor, right? But are you going to come back tomorrow or what? For how long do you want this charge to be held on the capacitor accurately?
I mean, small portion of the clock period.
Until the next time you do an auto zero, correct? So, if you decide to do an auto zero period, auto zero, every cycle, then leakage is really not a big issue. Okay. So this is one reason why you would want to make CAZ large. Another reason, the least important reason, is leakage, and just like leakage there is also charge injection, which is a lot more fundamental problem, correct. And if you try to make these switches which will dump charge, okay, so charge injection is smaller. One could argue that in this particular case that we have shown a single ended system, charge injection is a problem. However, in a fully differential system, charge injection appears as a common mode error, so it is not likely to be a big problem either. Okay. So the main reason for even attempting to have a large auto zero capacitor is simply the attenuation due to the input parasitic capacitance of the preamp. So why would you want to have a small, are there any reasons? Or are there any advantages to using a small auto zero capacitor? Clearly you making CAZ too small will result in the CAZ by CAZ plus CP to be much smaller than 1. Therefore there you do not want CAZ to be too small, and of course all charge injection effects will simply become a lot more severe when CAZ is small, and leakage, as he pointed out, also becomes a problem. But is there any advantage you think of using a small CAZ? Speed of what?
No, in the other phase, VREF P, VREF M, they have to charge these capacitors.
VREF P and
VREF M, they have to charge these capacitors.
Okay, so
switches
during the auto zero phase, please note that the equivalent circuit is this. So the amplifier has to drive a load equal to CAZ. So if CAZ becomes too large, what happens? In order to be able to settle, please note that we only have a duration equal to phi a z. During that time the voltage across the capacitor must settle to V offset times A by A plus 1, you understand. And you know that in any amplifier, if you go and increase capacitance, it will be slower, correct. For the same quiescent current, if you want to drive a larger capacitance, it means that it will take a longer time to drive it, correct. So settling time becomes larger, and therefore the only advantage, you want it small because settling time becomes smaller. So the only advantage to choosing a small capacitance is that the auto zero can happen quicker, you understand. So like in everything else, you neither want to make CAZ too small, which will cause significant attenuation of the input during the amplify phase, right, nor do you want to make it too large, right. If you make it too large, the attenuation problem goes away. However, the time taken for the offset voltage to settle onto the capacitor becomes very, very large, correct. And there is also a third effect which is not fundamental. It turns out that any capacitor you make will also have a parasitic capacitance called the bottom plate capacitance, correct. So one of these plates of the auto zero capacitor will have a parasitic which is say a percentage of CAZ. So, this is let me just take this to be 10% of CAZ as an illustration, alright. Now, if you go on increasing CAZ with the hope that this attenuating factor CAZ by CAZ plus CP becomes closer and closer and closer to unity, we find that this will also increase and this parasitic capacitance directly comes as a load to the sample and hold. You understand? So, the trade offs therefore are, you do not want CAZ to be so small that the input is attenuated too much, you do not want it to be so large that its bottom plate parasitic and becomes a big burden on the previous stage, and because of the large CAZ the settling time in the auto zero phase becomes very large, right. Okay. So, we will continue in the next class.